Okay, so yes, I'm going to talk to you a little bit about paleoproxies. So this audience is extremely diverse, I can see. So I don't know, it's hard to find the how to tune this, but so some of you probably know a lot of what I say, and some of you don't. But it's I'll do my best. Okay, where's my pointer? This is this one. Okay. So this is the Earth, okay? It's the Earth. It has a climate, for example. So we're discussing today, primarily I will talk about corals and coral skeletons. So biomineralization, of course, is a key word. How we reconstruct climate with corals, and sort of the ins and out of that, how well it works, how well it doesn't work, etc. Just to have some kind of critical view on that. And so the problem in general, of course, with proxies is for environment. This is not a very strong pointer, but I don't have it. Anyways, is that if you want to understand the climate and environment and how it evolves in the future, we need to understand how it was in the past. So we need to develop some kind of proxies for paleoclimates, okay, for how it was in the past. And so, what is a proxy? I just gave a class in my in a master's class. So I'm sorry. This is you do okay. So I sent you go to Wikipedia, of course, the first place you go, and you see that proxies are something that we can measure, okay, that is related to, for example, climatic variations, okay. And so to develop that into a proxy, that's some geochemical parameter, for example, but it doesn't have to be some parameter that we can measure in a record, in a geological record. We need to turn that into a proxy. We need to make sure that it's actually related very well to the environmental change that we are trying to reconstruct. We need a chronology, so we know when things are happening, and we need to have a sense of its precision. Okay, so how well it works. Okay, there's many other things, but it's to have a very good proxy, for example, depending on what the problem is, of course. But one other thing that you want is to have good coverage. So you want this proxy to be valid in many places, okay? So you can, have, especially if it's a global problem like the climate, you want to have something that is available to measure in many different places, to have the coverage of it. And so where can we look for proxies? You know this, okay? My students didn't, I think. For example, we can take a tree, okay? And we can look at the tree rings. Now the tree rings, we can simply measure their width. And so you see the annual, rings growing here, tack, 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 tack. And it's supposed to work this way, that if it's cold, the tree grows less. And if it's warm, it grows more. And so the width of these tree rings is supposed to be a measure of the climate. But, okay. Even a physicist knows. I'm a physicist too, so I can say that, okay? Even a physicist knows that, it's not just that it's cold or warm. Maybe it was dry too. So that maybe even there was a warm summer, but it didn't rain. So that's why the tree didn't grow a very thick ring. In other words, there are many different parameters other than the one we're trying to reconstruct that might affect the proxy, okay? Which is, in that case, is noise, okay? Something that can make a parameter change which is not directly related to what we're trying to reconstruct. Okay. All right, and that I'm going to talk to you about this problem in general, certainly now on corals. So corals, of course, and carbonates in general, which are formed by organisms in the marine environment. This is basically what we're talking about here now. There's many different proxies, okay? There's, different isotopic proxies, there's trace element proxies, etc., that you can measure in these carbonates that are formed by different organisms. The beauty of many of these carbonates, for example, foraminiferous or, whatever, corals is another example, is that they are, especially in the case of foraminiferous, they are present in the geological record, in the sediments in the ocean for for a very long time. So, you can probe them through a long part of Earth history. At least, I think for foraminiferous, it's almost 300 million years that they are present in the record. Now, For example, the oxygen isotopes. Oxygen isotopes is, of course, a very used proxy for changes in paleo environment, in climate, in temperature, in fact, of the water. What you have here is a graph where you have the temperature of the seawater, different organisms that live in the water, okay, and the difference in the isotopic composition between the water, okay, SMO with standard mean ocean water here, that's the oxygen isotopic composition of the water, and that of the carbonate formed by these organisms. Okay, there's a small little difference. Always, there's a little fractionation, as we say, so that when this carbonate is formed by the organism from the carbonate in the seawater, it changes the oxygen isotopic composition just a little bit. Okay. And then this isotopic fractionation is temperature dependent. Okay. This is already pretty good. Okay. So because if you want to reconstruct, for example, the temperature of the water in which these organisms live, here we have something that could potentially be a proxy. Okay. Because for a given, assuming that the oxygen isotopic composition of the water is constant, then the oxygen isotopic composition of the carbonate is going to be different than that of the water, but different in a different way depending on what temperature it formed at. Okay. There's a correlation, there's a relationship with the temperature. Okay. Now, I don't know what's next. Yeah. If you want to use that, let's say we take some foraminiferous that are 300 years old or 500 years old, and we measure the isotopic composition of their carbonate, we can assume pretty safely that the oxygen isotopic composition of the water was the same 500 years ago as it is now. Okay? And that's very important, because if the oxygen isotopic composition of the water changes, then everything changes. Okay. There's a shift. Okay. So when we reconstruct on long time scales, for example, if we go to millions of years here, 1 million, 2 million years, we have a problem immediately for this proxy, which is that we can no longer assume, in fact we know now that it's not true, that the oxygen isotopic composition of the water is constant. So all of a sudden, on long time scales, we go from these foraminiferous recording primarily temperature in the oxygen isotopic composition of their shell, okay, to actually recording fluctuations in the oxygen isotopic composition of the water. Okay. I'm just trying to say something halfway intelligent about the problems of these proxies. Okay, that there's different parameters, different effects that can go in and disturb it. So on one hand, if the isotopic composition of the water is constant, we could use this to reconstruct temperature of the water. But if the isotopic composition of the water changes, we are really the isotopic composition of the carbonate is really tracing that change of the water composition. And so this is, for example, the case here for the foraminiferous. On long time scales, there are huge fluctuations. You see them here in oxygen isotopic composition, which are way too big, by the way, to be driven by temperature alone. Okay, much too big. And what this is, of course, is a big fluctuation in the isotopic composition of the water of the ocean because of ice ages. Okay. So what happens when you have an ice age is that you have water evaporation from the ocean, which is going to be isotopically light. Okay, you know there's two isotopes, two primarily isotopes of oxygen. There's 16 and there's 18. Okay. Okay. When the water evaporates from the ocean, it's going to be light, because kinetically it's easier to evaporate oxygen 18 than oxygen 16 than oxygen 18. And this light water that is or vapor that is evaporated is going to precipitate and fall up and form an ice cap in an ice age. So the ice is light, but in an ice age there's a lot of ice produced, which leaves the water heavy. Okay. So when you then go back and forth between ice ages, the isotopic composition of the ocean fluctuates quite dramatically, several per mil, a fairly big change. And that is exactly what these forams are recording here. Okay. So on that time scale, these foraminiferous, these biocarbonates are recording basically global scale fluctuations. Okay. And this is, of course, quite fascinating. You can take a little form, a little tiny piece of carbonate like that at different times during the record and actually reconstruct sort of the beat of the planet on a time scale of millions of years and see how the ice ages, for example, have come and gone. Okay. So corals. Let's talk a little bit about corals, because this is something I actually know something about, maybe a little bit. Okay. Okay. So corals, of course, are also used to reconstruct climatic change, temperature of the water. And so here we have, I'll tell you a little bit how this works. This is a very nice, beautiful Parides colony. This is the coral that's most used for paleo reconstruction. You know, the corals are threatened, of course, by climate change, pollution, etc. There's a big problem at the moment. And it is true, it's a problem. And there's a big, there's what do you call it, bleaching, and the reefs are suffering a lot. In some places, though, when you go and you look at the corals, you see that they're full of holes. I mean, like this. And there's a lot of holes. And this is because geochemists have gone and drilled them, okay? So I'm wondering what the biggest threat is to corals sometimes, if it's the climate change or it's the scientist. Okay, but anyways, the point is that in this skeleton here, this is calcium carbonate skeleton, which is growing like an onion, like that. I'll show you in a minute. There is a carbonate forming. There are variations in the surface, in the water temperature, seasonally, of course. There's warm and cold. There is maybe El Niño, La Niña, etc., changing the climate. And this, if we can find something to measure, which is correlated to these changes in the skeleton, well, then maybe we can reconstruct those changes or those variations on the time scale that this coral has lived, which in this case, for this coral, which is probably 3 meters in radius, it grows about 1 centimeter a year. It's maybe 300 years, 400 years, which is very interesting, right? Because if you want to go for anthropogenic climatic changes and see the effect of the industrialization, etc., we are really interested in something that gives us a couple of 100 years before the whole thing started, the problem started, and then the modern times. So that could actually be recorded in a skeleton like that if the proxy is precise and if it works. All right, so a little bit about corals in general. Corals are everywhere. Okay, so we have good coverage. Okay, if you want to look to reconstruct climate and global climate change, it's very nice. This is essentially essential. We need to be able to go, certainly in the tropics, in the belt around the Earth, tropics and the subtropics, they're basically corals. Surface corals, the ones we think about that form the coral reefs. But in fact, there are corals everywhere. Deep sea corals that live down, in fact, as far down as the submarines can go, we find corals, basically everywhere in the ocean. Of course, the ocean is extremely stable. The deep ocean is stable, so it doesn't record on a short time scale changes. But I'll get back to that in a minute. So these different corals, they're called Sclerotinia and Corals. They are different species, of course, that have adapted to live in very different temperatures. We're only really going to, no, that's not true. We're going to talk about both types of corals a little bit. They form a skeleton of calcium carbonate. And of course, they've been used to record variations in sea surface temperature. So if you just talk about the reef-building corals that live in the tropics and the subtropics, and you know the coral reef that you know, through the variations in their trace element abundances and the isotopic composition, just as you saw before, the oxygen isotopes. Okay, I'm going to talk mostly about the trace element abundances.
Yeah.
Yes?
You said depth ranging from 0 to 300.
So they live from, in the tropics, the different species of corals, what you call them, the reef-building corals, they are basically at the surface of the water. And then you have deep sea corals, still belonging to the same taxa. I have to be very careful now because there are people from the museum. Okay, sure. And they are living down to, in the cold, deep ocean, and they are different. They're different species. There's a whole, and by the way, in the deep ocean, they can form reefs too. We talk about deep coral, cold coral reefs. It's not, but it's the same, organism, same family. Grosso modo. For a physicist, it's all the same. I guarantee you. Okay. Okay. So why is it important? Okay, just to get back to that, very quickly, of course, it's very important because to understand the sea surface temperature, variations in the sea surface temperature, because it's a very important parameter in global, what do you call it, circulation models. If you change the temperature of the ocean, of the surface water of the ocean, especially in tropics, by just half a degree, you increase immensely the amount of water, amount of heat that's transferred to the atmosphere, which is then transferred to the higher latitudes. So it's a very big parameter. Okay, in global climate models, I would say the two most important parameters in these models is that sea surface temperature and then cloud cover, etc., in terms of reflection and incoming energy. And so how does it work? Okay, I'll get a little bit into the machine room of using corals to reconstruct climate. So here's again one of these provided corals, which is going to have a hole in it. And this is not, it's big, it's a very nice big coral. No? It probably has a couple, 100 years or so in it in terms of so what they do, I don't really do it actually, but what people do is they will drill a piece of the skeleton. Okay, and when you drill into that coral here, you're drilling, of course, back in time. Not so much. What do I do? I hit harder or what? Attends, it's really okay. Okay, I do something. Where's my? I go like this one by one. It's going to be a long time. Okay. So when you drill a piece of that out, so here's about a 10 centimeter core. You can take a slice of that core and you can take an X-ray map of that. And what you see is very nice, beautiful annual growth rings. So here you have a beautiful chronology, right? Now, by the way, you do it too. You always show your nicest picture, okay? Okay. It almost never, ever looks that nice, okay? This is a perfect picture, okay? I'll show you some real pictures in a minute, okay? What?
It's a very nice color.
This is essentially perfect, the best picture I've ever seen, okay? I always use it. I only know one picture like that, okay? So, but it shows it brings the point home, okay? Namely that there is annual growth bands. So you have darker bands. This is actually, I think it's a negative X-ray image. So basically, dark means low density skeleton. White means high density skeleton. So basically what happens is in a warm period, in a summer period, for example, the skeleton will extend fast, building a relatively low density skeleton. And then in the winter time, it still calcifies, it still produces skeleton, but it doesn't extend as fast, and so it becomes a higher density thing. So basically what you can see here is that this coral here was drilled out in the spring of 95 here, probably. Then we have 94, okay. Now, what you then want to do now is you want to find something that you can measure in this skeleton that is related to temperature, okay. And another thing that's very important is you need to calibrate this, okay. You need to find something you can measure, and then you have to calibrate it against the temperature variations to see if there's any information there. And so what people usually do, what people usually do is that in order to obtain this calibration, they will have a temperature record, actually measurement of the water temperature for some period of time. In this case, for example, here you have, you've taken this skeleton, you have measured oxygen isotopes, the strontium-calcium ratio, or the magnesium-calcium ratio, and then you have the sea surface temperature measured with a thermometer right next to this coral. So there's no discussion. We know what the temperature was. And then you're trying to relate. I know, you've never seen anything that good, right? So again, it's the best example you ever will see. Okay. So you have here essentially a calibration. Okay. You have some kind of geochemical parameter. Let's just talk about the strontium-calcium ratio, because that's basically what I'll talk about for the rest of the talk. You have a strontium-calcium ratio that obviously evolves with the season. Okay, there's a signal, goes up and down in concentration. And by the way, the strontium-calcium ratio is negatively correlated with sea surface temperature, and so they swap to make the two curves follow each other. They flip the axis here. You see that it increases down. Okay, just to. And so that's a key thing, right? That's a key thing. This calibration, because a proxy, in general, is never better than its calibration. If you cannot calibrate extremely well, you cannot reconstruct, right? Because when you calibrate, you know everything. So here are 3 examples of a calibration of the strontium-calcium ratio in 3 different corals that lived, and these are very typical, and I'm not exaggerating in either one way or the other. Okay, this is typical quality of the calibrations in the literature of the strontium-calcium ratio versus the temperature in 3 different corals, these Porites corals, that lived in a small atoll in the Indian Ocean. They've seen open ocean circulation. There's no special effects of lagoons, etc. And so basically what you have here is the sea surface temperature, which is obtained some way, either a direct measurement or something. Yeah, probably a direct measurement right next to them. There are 3 corals, same species. They lived a few hundred meters from each other. They've seen the same ocean. And they've seen the same temperature. And what you see here is that the calibration, first of all, you see some noise. Okay, you see that the slopes are actually different. Okay, so this means that if you calibrate with this coral here, if you reconstruct from this coral, you're going to get a slightly different answer than if you reconstruct from this coral, of course, because that calibration slope is different. Okay. What you also see is the noise, right? If there was a perfect correlation, if this was really, this precipitation or this formation of this calcium carbonate happened in perfect sort of thermodynamic equilibrium. If you do the experiment in a beaker in your lab, you put some carbonate, you put some calcium, you have a certain temperature, you form a calcium carbonate, then you can change the temperature a little bit. You do it again. There's a little bit of strontium in too, of course. Then you in a lab you can produce a essentially perfect correlation between the strontium-calcium ratio in the carbonate you form and the temperature at which you formed it. Okay. But here we obviously don't have that perfect correlation. We have noise. These are the R-square values. Okay, so this is the goodness of the fit, if you want. It's a measure of how well a linear fit matches the data. Okay, a linear function matches the data. As you know, if R square is 1, all the data points lie on one line. If R square is dropping towards 0, it's because it becomes noisy and no longer basically a cloud of data. So if we have something that's decent, there's a linear relationship, there's no doubt, but you also see a lot of noise. Look, if you measure, in this coral, for example, in some place you measure a strontium-calcium ratio of 9.2 millimole per mole, it could correspond to 28 degrees, or it could correspond to 24 degrees. Okay, just from the noise in the calibration. In fact, there's some random number in between, right? And so this is, of course, a problem, right? Because and it becomes a problem only, of course, in relationship to what we're trying to reconstruct. If we are trying to reconstruct something which changes by 30 degrees C, well, then if you have a plus or minus a couple of degrees C of uncertainty or noise, it doesn't really matter. But if you're trying to reconstruct something that is only on the order of 1 degree C, you better have a proxy that is significantly more precise and accurate than that. Okay. Okay. So you get the drift. Okay. All right, so just to get you it doesn't really matter all this stuff, but just to get you a little bit of a feeling of this, because in the literature very often you don't really have a big good evaluation of what the precision is. You see a calibration like that, maybe you don't even see the data, you just see a slope, a linear equation with a slope, and you get an R-square value. Okay, and then you say, oh, the R-square value is nice, so it's good. But it would be nice to understand a little bit about what it means, this R-square value, in terms of the noise in the system. Okay. So without going into too much detail, okay, I just want to say that you can do this very simply. I just did a very little experiment, funny experiment, trying to introduce noise on the temperature to see how the R-square drops. So here's a perfect linear correlation between a strontium-calcium ratio and a sea surface temperature. Here's I just took some equation out of and slope and different constants for this equation out of the literature for some coral I found. Take some random numbers here between 22 degrees C and 29 degrees C. Take a random sea surface temperature. Use this equation to calculate the strontium-calcium ratio. And you do that a couple of times. Then, of course, they all fall on that straight line because I just calculated them too. Okay? And the R-square value is 1. Now we can do the same exercise. We can begin to introduce a little bit of noise, random noise, on the temperature. So what I've done here, this is what we had before. Everything is calculated to fall on that line. Now we do the same thing, same slope, same equation. Take random numbers, calculate the strontium-calcium ratio, and then afterwards add a little bit of noise to the sea surface temperature. Okay. So here I've added just a randomly with an amplitude of 1 degree C. I've added a little bit of noise. So first you take the temperature, you calculate the strontium-calcium ratio, and then you add some random noise, which is maximum plus or minus 1 degree C. Okay? And this does what? This puts the R squared to 0.94. Okay? Plus or minus 1 degree C random noise is 0.94. If you do plus minus 2 degrees C of noise, it becomes 0.76. And of course it gets worse and worse. Okay. So you see, just to get a feeling for the noise and the corresponding R square value. Okay. And this, of course, you have to put in relationship with the effect we're trying to reconstruct here. If we take a coral, for example, we have the sea surface temperature variations, for example, through the last 100 years. Okay. But here I think everybody would agree that that effect still is no more than 1 degree C maximum. Okay. So you have to ask yourself, if you take a coral and you make a hole, it should be a purpose, right? Before you make a hole. When you make that hole to pull out that skeleton, you're going to actually get something, a proxy that is precise enough to reconstruct a 1 degree C change, for example, over the last 100, 150 years. I think for the corals, you get the drift, right? I don't think we can do that. So here's some records from reconstructions from the strontium-calcium ratio for a long time. So they probably here, if I remember correctly, they have taken different corals. This is not one long coral, okay? They've taken different corals, some corals that probably died earlier, etc. And they try to reconstruct to do the best. And maybe some of the corals actually cover the whole period down to, a couple, 300 years back. But, yeah, I don't know. If you see the Industrial Revolution here, it's tough, huh? No, but we're scientists, right? That's it. This is what we do. Okay. Now there's also this was strontium calcium. There's also oxygen isotopes. How much time do I have to talk, by the way? Because I can continue.
45 minutes.
I have
40 minutes.
Left or total? Left. Oh, oh, it's very nice. Here I'll just give you another example, okay? Because what I'm getting to, of course, is that I talked about before this thermodynamic relationship. You saw the noise, which would give you a thermodynamic relationship, which would give you a perfect correlation if you do it in the lab. Okay, if you precipitate this calcium carbonate in the lab, versus the noise you see in the coral. Okay, but of course it's a living organism. Here's another example where the oxygen isotopes. It's not very clear, but what we have here is temperature variations throughout the years. This is 1982, this is 2002, of the East Africa and the Seychelles here. And what you see in 98 is the biggest, I think the biggest El Nino temperature anomaly, certainly for that big region, in 100 years. Okay, it's a big, almost 2 degree, increase here because of El Nino. So Aldo Shem is a good friend of mine. He's at the Weizmann Institute in Israel. He's a smart man. He said, okay, I will go in 2000 and whatever, 4 or 5 or 6. I will go to the Seychelles and I will drill some more holes, okay, into these corals, and I will see if they have recorded the biggest El Nino event in the oxygen isotopic composition, the biggest El Nino event in the 100 years, okay. So he did that. Oh, la, la. This thing, he gave me these slides. I don't know how to remove this thing that moves, and So he went there. He says it's a very nice island. He recommends this hotel here on the left, and he comes in on a small plane. He goes. He drills corals. Huh? See, there are holes everywhere. Okay, tack, 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 tack. Now it looks more normal. By the way, you see the skeleton here. Doesn't look so nice. So this is more. You see the growth bands, but it's a little more normal. Okay, it's not so nice as the first one I showed you. So here he has, just to show you that he actually took a skeleton. He measured the oxygen isotopic composition, which is these things in yellow here. Forget the carbon-13 right now. But the oxygen isotopes are supposed to vary with the sea surface temperature. the temperature of the water, right? And they do. You see, there's seasons here. There's no doubt about that. Now, he took six cores, and I'm just going to go through them one by one, and then you can tell me, we can decide together if there is a record of the biggest El Niño event in 100 years, okay, in these. Here is the sea surface temperature, and it's very nice actually. Up, El Niño, okay, in black. This is the El Niño event, okay. It's a pretty big event, in fact. Here is one core in oxygen isotope composition. First of all, it doesn't really follow that well, but okay, anyways, it goes pop, 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 pop. If you didn't know anything, you would say, something anomalous happened here, right? There's no doubt. There's something happening. Let's take the next one. No, you would not be able to tell, right? This one, give it half a point, okay, half a point. This one, no. This one, no. This one, no. Okay, 1.5 out of 6 corals recorded in the oxygen isotope composition, the biggest El Niño event in 100 years. Yes?
The point is, which is the source of error? Because until now you are talking about statistics.
Yeah. So.
But it's very important to know.
So, exactly. Very good claim. So, what? Okay, you have 40 minutes after me. So, no, but the problem, look, there are many different factors. The real problem is that it's not a thermodynamic experiment in a beaker. It's an organism. And as soon as you say the word biology, the shit just hits the fan, okay? No, it's a nightmare, okay? It becomes basically psychology, okay? No, because I'm making fun of it, but you know, maybe these corals that did not record this El Niño event, the temperature was simply so high that they were so stressed that they didn't actually build much skeleton in that period. Maybe there's no record at all. Okay, maybe I don't know what, but the point is that there's, as soon as you put in, that's your area of uncertainty, that's your major source of uncertainty, biology. We don't know, and that comes back to this problem of the biomineralization process and all the things we don't know. We don't really know how this biology is affecting and, you know, controlling the trace element composition and the oxygen isotope composition or the stable isotope composition of the skeleton. But for sure, you know, the environment affects it, and there is a record of the seasons. There's no doubt about that. I'm not saying that it's complete nonsense. Okay, there's no doubt. There's seasonal variations. The question from a paleo reconstruction perspective is how how precise is that proxy, and how precise can you reconstruct? And the problem is that these are living organisms, okay? And this is the main error of uncertainty, in my opinion.
You mean that imagine that the living organisms do very well.
Yeah.
Okay? It would be any way to explain that kind of, let's say, error due to anything during the protocol of measurement?
Oh no, it's not the measurement problem. This is one thing. No, okay, sorry. No, there's no way we can measure the oxygen isotope composition or the strontium calcium ratio to a precision that is much better than these differences here. This is for sure. It's not an analytical problem.
No, but this is a kind of precision, not necessarily kind of resolution. This is two different things. You can measure very well, okay, but not to measure the real thing, the real point.
No, okay, then okay, you're talking about where in the skeleton versus when you do the calibration, or I'm not sure I understand you.
I'm just saying, I mean, to try to understand where are the source for error in any, in the whole protocol.
But I don't think there error in terms of analysis.
The size of the sample, for instance.
Oh, but that's okay.
Carbonate.
You know what? I'll show you, because that's a very good point. The size of the sampling, for example, I'll show you. Now, just to say one more time, it's not that there's no signal. Huh? It's not that this is again sea surface temperature versus the oxygen isotope composition in a coral skeleton. There is clearly a seasonal variation that correlates with the temperature. Okay, but you also see that there's some big mismatches. Okay, for reasons that by and large we don't understand. Okay, and this is again, this is not an analytical problem in the sense of precision of the analysis. That's for sure. Okay. Okay, some more reconstructions. Yeah. Okay. So what now? I'm going to address some one of the things you mentioned there. What I'm going to do now, I'm going to try to go and look into these skeletons of these corals at a smaller and smaller scale, and try to look at the trace element composition. And there's also some oxygen isotope data in there to see what we see when we go and dive into the ultrastructure of the skeleton, to try to get a feeling for what is this biology, what's going on. No, I don't think I'm not going to tell you how it works. Okay, I'm just going to document what's inside that skeleton and what might be the source of the noise that's that destroys these correlations, if you want. Okay. So here is a nice skeleton of Porites, this coral that is most frequently used, and just give you an overview over the architecture of a coral skeleton, just very briefly. And so it's all aragonite. It's a calcium carbonate. It's formed by these individual polyps. They're sitting as a colonial organism. Individual polyps here. One is forming this corallite here, we call it. Here's another one here. There's a wall around it. See here, and then there's these septa that sort of stick into it, like divisions like that. I have another species which shows it much better because Porites is a very, ornamented skeleton. Here is a Pavona species where you see the wall very clearly, and you see these septa that stick in here. Okay, so this is sort of an overall organization of a single polyp, which is on the order of a millimeter or so, depending on the species, of course, something on the order of a millimeter, and grows this way, okay, out towards you, okay, because it's now, if you take, let's say you make take a thin slice of this septa here, and you look at it in transmitted light, polarized light, you see this, okay. So you see basically, and here's an SEM, scanning electron microscopy image of, it's not the same region, of course, it's not the same piece, but of an etched surface of the same part of the skeleton. What you have here in two different ways, you see the sort of the two main ultrastructural components of the coral skeleton. You see these little black dots here, like that, or here they are, okay? We call them centers of calcification or rapid accretion deposits. There's different ways of calling this, but they are basically, you can think of these as the distribution of these centers of calcification they're put down in the center of the septa like this, and along the wall, and that is sort of like the starting point for the construction of the skeleton. This is a caricature, okay, but like this, and then overgrowing these, forming on top of these, is this fibrous aragonite material here, which gives the skeleton its bulk, mass, and its strength. Okay, so there's these two components: the centers of calcification and then this fibrous skeleton. Now, what we're going to look at now, we're going to look at this structure here with ion microprobes. Okay, so this is the tool I use the most to analyze trace element and isotopic composition. And I'm just going to show you, talk to you a little bit about this. Many of you know how this works, but some of you probably don't. So I have to tell you a little bit about how these machines work, so you can understand how the data are generated. So for one of the tools we use is like the nanosims, like we have here in Paris in the Museum du Star Naturel, which is an ion microprobe, which can do a very, very small spot on the sample and measure certainly trace elements on a very, very small scale. So we can resolve these structures that you just saw, these small structures. Now, okay, the ion microprobes, what does that mean? It means that we are probing the sample. You take a coral, you polish the sample, it's a skeleton we are shooting at. We are probing the chemistry or the isotopic composition of this by bombarding it with a beam of ions. So we are probing the sample by bombarding it with ions. So it's an ion microprobe or an ion probe. And so, so we are shooting, anyway, it doesn't matter. This doesn't matter either. We are shooting on a sample. We are sputtering knocking off atoms from this sample. A fraction of these atoms are going to be ions coming off. We call them the secondary ions. So we have a primary beam of ions that hit the sample. It generates a beam of secondary ions from the sample. And those secondary ions we can analyze in a mass spectrometer to analyze, for example, trace element composition. So there's a little movie here we have of how the nanosims, for example, works. The sample sits here. The primary beam is generated to hit, coming in and hitting the sample here. It doesn't normally glow. Okay, if it glows, there's a big problem. This is for artistic, you know. Here we have a very special sample that consists of yellow and blue and green atoms. Okay, we hit the sample. We can generate images by rastering this primary beam across the sample. Atoms are flying off. A fraction of these atoms are ions, and those are the ones we can work with, of course. We are extracting those ions. You'll see they're extracted here. We're separating from the primary beam, catching them again, sending them into the mass spectrometer. They go through the magnet, and they're sorted according to their color. Okay, all right. So and so you know, it's a normal mass spec. Okay, an ion that flies through a magnetic field feels a force, and it turns. Okay, and the heavier ion is more difficult to turn than a light ion. Okay, and that's why they come out of this magnet sorted according to their mass, grosso modo. Okay, so and in this machine there's 5 detectors. You get from the same small spot on the sample, you can pick up 5 different ions. So for the purpose I'm going to show you now, for example, you could have a calcium isotope that you could measure here, calcium 40 or 44, and you would have a strontium isotope here, and then that way you can form a strontium to calcium ratio, which we can relate to a strontium calcium ratio of a standard that we know, and then by walking across the sample, you can actually measure the strontium calcium ratio with a very small beam. Okay, and then so this is what I'm going to show you. Okay, so here is an example of a coral. Now this is a reef-building coral. Okay, this is a coral that lives at the sea surface. Okay, look at the scale now. Okay, this is 100 microns. Each of these beam spots are 20 microns. Okay, so this is not the nanosims. This is a conventional ion microprobe that has measured this. If you look, this is the skeleton here. Okay, this is epoxy out here. It grew this way. Okay, this skeleton, and this is all skeleton. This is a very small length scale here. So this is skeleton that has formed in a fairly short. They grow pretty fast. Huh? So this is skeleton that has formed on a time scale, I would say from here, growing this way up, no more than 24 hours, okay, probably. Okay. In other words, the sea surface temperature has not changed, okay, here. It's pretty clear that the environment has not changed radically in 24 hours, so let's even make it 36 hours, okay. What we've done here with the ion probe is go back from the fibers, these fiber regions of the skeleton, into what we call the centers of calcification. You see two of these structures here, okay. So basically we're shooting into the center of calcification out on the other side, and the same over here. Now look at this data here. So basically we have here, this is magnesium concentration in the skeleton, and here was the biggest difference. So this is the one that really separates these two structures, because you see the fibers have a relatively low magnesium concentration, and then as soon as you enter into these centers of calcification, boom, the magnesium calcium ratio, the magnesium concentration goes up by a lot. Okay, and so we plotted that against strontium. You can also see that there's also a difference in strontium. This is an uncalibrated raw ratio between boron and calcium. Boom, boom, boom. In other words, if you go across from one structure to another in skeleton, in a reef-forming coral that has formed within 24 hours, you see from one ultrastructure to another very dramatic trace element variations, which obviously cannot be driven by temperature, because the temperature simply hasn't changed much in those 24 hours. Okay? You see the problem? So here is in the same trace. In the same trace here we have measured the oxygen and the carbon isotopic composition. Here we have the fibers, and here we have the centers of calcification. They're a little more scattered, but they are clearly lighter in oxygen isotope composition. Just for information, if you do a calibration of the oxygen isotope composition in a carbonate in a beaker in a lab, 1 per mil difference, which is a small difference but easily measurable, corresponds roughly to 5 degrees C. Okay? So in other words, to go from here to there, the temperature would have to change 15 degrees C. Now, obviously, that did not happen. Okay, yes?
But you're not considering chemical fractionation.
Oh, chemical fractionation.
Because you know, for sure, the growth rate and let's say the precipitation, mass precipitation,
Yeah.
in two different extractions, the fibers in what you call COC,
Yeah.
are different.
No, but there's nothing that can, you know, you mean a kinetic fractionation or something?
Yeah.
To do that on for 5 per mil?
I don't know. I mean, I'm not an expert.
I think it's.
I'm just thinking, you know.
Yeah, we don't know exactly the mechanism. You do, but I don't. Okay, but it's obviously something is changing. Maybe, I mean, what we're getting back to here is probably, in my opinion, there are cellular level processes. Okay, because there are certain cells maybe that form these things. You don't think so? There are certain cells that may form these things, and other cells that form the fibers. Maybe they're using different reservoir, internal pools of oxygen. I don't know. Okay, I simply don't know. Maybe there's metabolic signatures in the. Yeah, I don't know. Okay, the bottom line is this is not temperature. From a paleo reconstruction perspective, that's really what matters. Because if you're a paleo reconstructor, you can say I don't give anything about biology. I just want a nice calibration. Right now, we're just trying to look into what is the source of the noise. Here is another example. This is with the nanosims this time, because you see a very short time scale, 50 micrometers, and a lot of data. You go in a line scan across here. We are taking a deep sea coral from 2,000 meters. Now, if you ever want a stable environment where the temperature doesn't change, you go to 2,000 meters in the ocean. Okay, you can be pretty sure the temperature doesn't change. And so this is the annual max range. Okay, at this depth in this place, which has been measured. And so here you go again. You see the magnesium-calcium ratio, and you from the fibers into the centers of calcification, boom, it goes up and down again. Okay. Whatever it is, this is an expression of strong biological control over the trace element composition of these different ultrastructures, which is not related to the temperature. Okay. Here's another example: deep sea coral. Look at these variations in oxygen isotopes. Okay, they're enormous from a temperature perspective, just absolutely enormous. Okay, this is impossible. This would be 25 degrees C variation at 700 meters. Okay, you have to hit the Earth with an asteroid to do that. Okay, all right. Anyways, we can go on and on like this. It doesn't matter. You know, here's the centers of calcification. Here are the different layers in the fibers. You can see there's very strong beat of the magnesium-calcium ratio that corresponds to the layering as these fibers are put down. Okay, there's also variations in the strontium-calcium ratio, which is clearly above the noise, etc. It goes on like that. So the point is, and I'll finish. The point is that we have these skeletons. Essentially, none of the skeleton is really in equilibrium with the seawater, really for real. Okay, in a thermodynamic way. We have different ultrastructures which are dramatically different, both in trace element chemistry and isotopic composition from fibers, which are really formed. I mean, you know, we have a center of calcification, and at the same time, right next door is forming fiber skeleton. So it's not even really, it's not really separated in time. In terms of temperature variations, you cannot change the temperature in that short time scale. But in fact, it's forming almost simultaneously. Okay. And yet, you have these enormous differences in both isotopic composition and trace element chemistry, and which are not related to sea surface temperature. And so this is biology. Okay, and I'm not going to pretend I know how it works. Okay, I don't know. Okay, I don't. But it's there, because this is obviously not thermodynamics, and it's a real problem. And it's not just for a paleo reconstruction perspective. This is obviously a big problem, okay? And it's something we cannot really get rid of. Now, you had a very good point before. You can sort of handle it by sampling bigger chunks of skeleton. If you sample bigger chunks of skeleton, you get a nice average, okay, which will dampen some of all these. This is what I'm supposed to end with. It doesn't matter actually, but which will average out all this variation. Okay. And this, of course, is what people do when they reconstruct. If you go all the way back, okay, to Aldo here, okay, Aldo Schemes, who's done this, when he samples this skeleton, he does it with a dentist drill, okay, like, you know, which is 1 millimeter sized sampling. It's a huge volume compared to the tiny little spots we make with the ion probes, okay. So he's, of course, averaging out a lot of the noise, okay. But still, you know, you saw the calibrations. If you go all the way back, yeah. Still doing that, this noise, this biologically rooted noise, survives, and that is a problem for paleo reconstruction. It's not just a problem for the corals. It's a problem for just about anything that involves the word biology, which is why you should be a physicist. Thank you for your attention.